Okay. So this was our last example. So last time we talked about the system and it had no solution. So having no solution means that you remember that the space generated by these column vectors 1, 2, 3, 1, 0, 1, and 1, 3, 4. The space, well, to be precise, the span of these three column vectors does not include the column vector on your right. So this is, well, our column picture of having no solution. Okay, so today let me generalize this. So in general, I suppose that I have n equations and n unknowns. And this system of equations can be translated to, well, a linear combination of column vectors, linear combinations of these columns equals to the column on the right, just like this. And there are two singular cases. The first case is no solution. Having no solution means that the span of all these vectors does not contain the column vector on the right. So having no solution, so that was our column picture. So what does it mean? So in order to do this, so that means, well, clearly this is a subspace of n-dimensional Euclidean space. And this set does not have this guy as its member, means that this guy can never be the same as Rn itself, right? So in other words, this is a subset of Rn, but this guy can never be the same as Rn. So in other words, this is a proper subset of n-dimensional Euclidean space, right? So so this is our first singular case. And the next singular case is infinitely many solutions. 네? 왜냐면은 얘네들이 n-dimensional 벡터들이잖아요. 그렇죠? n-dimensional 벡터들의 리니어 콤비네이션으로 만들 수 있는 모든 벡터들의 모임이잖아요. 그렇지? 근데 얘의 모임에 속하지 않는 n-dimensional 벡터가 하나 존재하고 있어. 그 얘기인즉슨 이 친구는 절대로 Rn 자기 자신이 될 수가 없다는 거죠. 그렇죠? 그렇죠? 네. So maybe so 1 times x plus 2 times y and 2 times x 4 times y. This is a TOE example. So what is the column space of this? Sorry. What is the span of columns of this system? 1, 2, 2, 4. But as you can see, as you can clearly see from here, well, I don't need this because the second vector can be achieved by the linear combination of the first vector. So this is just span of 1, 2, right? And this is what? Is it R2? No, this is just a small, tiny little line contained in R2, but not R2 itself, right? So in this way, so in this sense, I say this guy can never be the same as R2. So this is a proper subset. This is a subset, but not R2 itself. So, and this is what I mean by the proper subset. And clearly, this space does not contain the column 2, 3, right? So, and this is my column picture explanation why this guy has no solution. Okay. All right, good point. Thank you. Now, the second singular case is sometimes you have a system that has infinitely many solutions. I will give you an example. 2, 3W, 3U, V, 4W. Okay, interesting. I have 3 unknowns and 3 equations. So typically, I should expect I should be able to pinpoint one exact solution from the system. But in this case, no, it's not. Why? Because just try to add the first equation to the second equation. Then the result is going to be exactly precisely the last equation. So in other words, I have only 2 equations, even if I have 3 unknowns. So I have 3 unknowns and 2 equations. So I may not be able to find out one exact solution. So usually in this case, you should expect a bunch of solutions, not just one solution. Okay. Let's try to find the solution of this. But I will not give up. So not being able to pinpoint a single solution does not mean I should give up this question. So I will do my best to find a solution of this system. How? Well, let's do like this. Let me multiply this first equation by -2 and add it to the second. Then I get -2v is 1 minus w, right? Yeah. Okay, so v is 1/2 w minus 1. Okay, all right. Now what? I will replace this v by this expression. Then u plus 1/2 w minus 1 plus w is 2. And solving this equation for u, I should get -3/2w plus 5/2. Am I right? Yeah. Good. So my solution vector, which is uvw, has to be is -2/3 w plus 5/2 and 1 over 2, v minus 1 over 2, and w is just w. Okay, and let me rephrase this. Like w multiplied by column vector, this column vector, and plus 5 over 2, negative 1 over 2, and 0. Okay. Well, here, so well, therefore, well, there is actually no restriction imposed on the unknown w. So just plug in any number you like. W could be 0. This one could be 1, minus 1, or millions or billions, whatever number you like. Then that number is going to be the solution of your system. So in this way, I should say, this solution has infinitely many solutions. This equation has infinitely many solutions. Okay. Well, by the way, so I have written down the solution in terms of w plus some other vector, other constant vector, but there is no reason that you should stick to the unknown w. Maybe you can try to write down the solution in terms of u or v, whatever unknown you want. But anyway, the point is that the solution set remains the same, no matter which unknowns you choose. Okay. All right. Then why? Can I give you any column picture explanation of infinitely many solutions? Well, the reason is very simple, because in this case, this equation, this system, well, especially the left-hand side of this system is precisely the same as this example, right? The only difference is the right-hand side, this 256, 257. So this last number is the only difference. So that means just try to imagine the span of columns generated by 1, 2, 3, 101, 1, 3, 4. Is it R3? No, it has to be less than R3, right? It has to be, well, precisely, this is two-dimensional space. And this time around, I had no solution because the span of these columns, which was actually a two-dimensional plane, this guy was not in that plane. That is why you were not able to find the solution. But in this time, I was able to find the solution. Not one, but infinitely many solutions. So why is it possible? Because, well, by accident, this guy, 257, happens to be inside the plane spanned by these three columns, right? So that is the only explanation. Okay. Right. So let me summarize this. Given a system of equations, system of linear equations. I have this system of equations, and I can classify the problem into three different scenarios. The first case is non-singular case. That is, the system has a unique solution for every possible choice of the column vector on your right. This is the first possible scenario of this given linear system. So when is it true? This is true only if right. Oh, yeah. I've never mentioned about the linear independence. Okay, good. Yeah. Yeah, right. Each vector, the n vectors are independent. So being independent means that the span of all these columns precisely forms the entire ambient space Rn. In this case, no matter which vector you choose from Rn, that guy should be achieved by linear combinations of these columns. Right? That has to be the only possible explanation. Okay? Okay, this is a non-singular case. This is the most likely scenario. Now, let me turn to the singular cases. Number 2? Yeah, number 2. No solution. It has no solution. That means having no solution is the vector on the column vector on the right is not a member of span of these columns. And in this case, the span of these columns should be strictly less than the ambient space Rn, a proper subset of Rn. And lastly, the infinitely many case solutions the system has infinitely many solutions only if in this case, the span of all these columns is not the Rn. Actually, this is a tiny small little fraction of this whole entire space, this ambient space. But if you're so lucky enough so that you have chosen this vector as a member of this guy, in that case, this is very unlikely scenario, right? This is the entire space, in the entire ambient space. And if this guy is less than this, then the dimension of this guy should be less than this. So in this case, if this is my entire space Rn, then span of this guy should be just tiny little fraction of this, right? And if your Bn, the column vector on the right, happens to be precisely in this plane, then you can find the solution. And in that case, the solution is not one, but infinitely many. Okay? Yeah. All right. Okay, so yeah, that is that. Now so let me turn to the next section, which is about the Gauss elimination or Gaussian elimination. For u minus 6b negative 2 is 9. Yes. Okay, what is Gaussian elimination? Gaussian elimination is a systematic procedure, or I should say systematic algorithm. So the Gaussian elimination is an algorithm that solves most of system of linear equation that consists of n equations and n unknowns. Okay. Let's take a look at this example. So suppose that you are supposed to solve this system. What are you gonna do? If I were about to solve the equation, well, then maybe I will try to solve the first equation for W and plug in that W into the other equation and try to reduce the number of unknowns from 3 to 2 and so on. So, well, this is what I did when I was a middle school student, a high school student. But that is not, I cannot say that is a systematic way to solve the system. So, well, in order to be precise and well-defined algorithm, then you should be able to invent some very concrete and specific way to solve the equation. So Gaussian elimination is like this. Sorry. I changed my mind. In order to introduce the Gaussian elimination, I will need to first introduce what do I mean by elementary row operations. Yeah. So before I introduce Gaussian elimination, I will need to talk about the elementary row operations. So what is elementary row operation? So elementary row operations is a set of bunch of operations that is applicable to given system. So what is that? The first operation is multiply any equation by a non-zero number. And the second elementary row operation is add an equation to another. The last operation is to exchange the order of rows of given system. So this is the elementary row operations, and these operations can be applicable to any given system. So here, each of these equations, they are rows, and maybe I can multiply any non-zero number to this, and add one equation to other and exchange the order of the rows. And what is the point of all these operations? So most importantly, apply these elementary row operations to the system does not change the set of solutions of the original system. Right? No matter how many times you apply these operations to the original system, the set of solutions remains just unchanged. Okay? Yeah. Do not change the set of solutions of the original system. So now what is Gaussian elimination? The Gaussian elimination is by using elementary row operations, Gaussian elimination changes any given system into so-called upper triangular system. So what is an upper triangular system? Upper triangular system is system of linear equations consists of n unknowns and n equations, but whose coefficient below the diagonal equals to 0. That is what I mean by upper triangular system. And by using our elementary law operations only, you can always try to convert any given system into the upper triangular shape. So I'm going to show you how. Yes, this is the original system. And I want to change it. I want to transform the system so that it looks like an upper triangular system. In order to do that, my first target is to eliminate these two numbers, 4 and -2, just by using elementary law operations. How can I do that? I can do that because, well, divide 4 by 2, which is 2, right? I multiply the whole equation, the first equation by -2 and add it to the second. Then I can eliminate the first one, this number. And by same procedure, I multiply everything by 1 and add it to the second. Then I can safely eliminate this number. So this is the -8 -2. Is it -12 and 8? And is it 3W? Yeah. Yes. Okay. So this is my first step. Okay. Oh, this one already looks. This one is almost upper triangular shape. But in order to be an upper triangular system, then I will also need to eliminate this number 2. How? By multiplying this guy by 1 and add it to the second, add it to the last. Then I can eliminate this number. So this 2u then this guy goes to 0, and this one is 1. And this is not 14, this is 2. Yes. Now, okay. Is it upper triangular system? Yes, because every number below diagonal equals to 0. So this is a upper triangular system. And this procedure is called forward elimination. So once you're done about the forward elimination, and how do you get the solution of this system? Well, this is easy. Well, so you must realize that the solution set of this guy is the same as the solution of the original one. And in this case, finding a solution is very easy. So, okay, let me go back to the very last equation, the equation on the bottom. Then it said, well, W is clearly 2. Now I have W equals 2. Then I plug in W equals 2 to the second equation. Then is it? And V has to be what? 1? Yeah, V must be 1. Now I have W and V. Plugging in these numbers into the first equation, I have U has to be 1. And so in this way, I have a solution. This last step, also starting from the upper triangular shape and finding the solution, this step is called the back substitution. And these numbers, these coefficient, that is, and on this diagonal, especially these non-zero numbers on the diagonal, they are called the pivot of the system. So this is a non-zero diagonals called the pivot. Okay, all right. Okay. Just a little digression. Well, so Gaussian elimination, the algorithm of the Gaussian elimination consists of two steps, roughly speaking, two steps, the forward elimination and back substitution. Obviously, forward elimination costs more computation power. How many computations do I need in order to perform the forward elimination? That is actually a very important question because, well, linear algebra is probably the one most important thing in computer science. Well, as for mathematicians, I regard linear algebra is very important, and well, I should be worrying about the time complexity of the Gaussian elimination algorithm. How many computations do I need? That is a very interesting question, right? I should say, sorry, forward elimination. In this case, okay, let me go back to the original system. This system consists of 3 equations and 3 unknowns. And speaking of time complexity, in computer science, there are essentially 2 different operations between numbers. The first one is addition, and the second one is multiplication. Which one do you think costs much more? Yeah, obviously, multiplication costs much more. Multiplication requires much more computing power than addition, right? So in this case, well, I will only consider the number of multiplication that is required to perform forward elimination. So first, in order to get rid of these 2 numbers, how many multiplications do I need? For simplicity, let me just ignore the right-hand side. Then here, well, dividing this guy by this, it turned out that I will need to multiply everything by -2, right? And I have to multiply -2 here, -2 there, and -2 here, right? So I will need to perform 3 multiplications just to get rid of this number. And by same way, I will need to get rid of 3 multiplications just to get rid of this. So generalizing this, oops. In order to get rid of these numbers, sorry, I have n numbers here, I have n numbers there, and just get rid of these numbers, how many multiplications do I need? I need n times n minus 1 multiplications, right? Now, how many multiplications do I need just to get rid of these numbers? I will need n minus 1 times n minus 2 multiplication, right? Da da da, all the way up to 2 times 1. So I will probably need this many multiplications just to do the fourth elimination, right? And so summarizing, I will need this many multiplications just to perform the fourth elimination of any given system consists of n equations and unknowns, right? What is this? So this is 1/3. So, well, if your n is large enough, then, well, this number is most likely 1/3 times n cubed. So in other words, the time complexity of this algorithm is n cubed, n cubic. Well, is it good or bad? Well, I don't know. Some people might say this is not an exponential algorithm, so this is a feasible algorithm, tractable algorithm. But, well, a cubic polynomial time complexity is, well, usually, I don't know, not that great. Is there any better algorithm than Gaussian elimination? I don't know. Well, I'm not a computer scientist. Okay, so anyway, so this is the time complexity of the fourth elimination. Okay. All right. Oh, here I have written something that looks like a matrix. Yeah, I know. I have never introduced formally, officially, I have never introduced the matrix, but I will also need our convention. Conventionally, we write if you take a close look of this Gaussian elimination algorithm, then you will realize these unknowns, U, V, and W, they do nothing. They're irrelevant in Gaussian elimination algorithm, right? What really matters is just the numbers, not unknowns. So I can just drop all these unknowns. So in some textbook, they write Gaussian elimination just like this, dropping all unknowns and leaving coefficient alone. 5, -2, 9. Well, I have put this one vertical line here just to differentiate the right-hand side and left-hand side. Okay, so this is sometimes we use this notation rather than this. I think this is more concise and, well, concise. And so therefore, in some textbook, some people they try to say, we apply the elementary law operations not to the system of equation, but to the matrix. But that is also possible, right? You can still apply the elementary law operations towards this looking matrix. So after a bunch of applications of Gaussian elimination, so sometimes this is called the augmented matrix. Sorry, I will introduce matrix a little bit later. Is Gaussian elimination always possible? No, there are some cases that you cannot apply forward elimination. In such cases, case number 1, U, V, W, 2U, 2V, 5W, and 4U, 6V, and 8V. Well, I am not that interested in the right-hand side. So let me just leave it the stars. Suppose that I have this system, and let me try to apply the forward elimination algorithm to the system. And first, I want to eliminate these two numbers. In order to do that, I multiply -2 to the first and add it to the second, and I multiply -4 and add it to the third. Then I get this. U, V, W, and 3W, and 2V, 4W, and star. So I have this. Then in this step, I cannot proceed anymore, because in order to proceed the next step, then I will need to divide this number by that number. But here, clearly, well, there is invisible 0 here. So you cannot divide the number by 0. So Gaussian elimination has to be stopped at this point. But this problem can be easily avoided by how? By exchanging these two laws, right? And conveniently enough, two exchange laws is a part of the elementary law operations. The 2V, 4W. So for the elimination step is doable in this case. So this is, even though it looks like the Gauss for the elimination has been broken down, but this is a non-singular case. So Gaussian elimination is doable in this case. However, the more fundamental problem arises in the second equation, second system. U, V, W, star, 2U, 2V, 5W. They are the same, but 4U, 4V, and 8W. Applying the Gaussian elimination, then it turns out 3W and 4W, right? In this case, no matter how many times you exchange the order of the laws, but having 0 number on the diagonal is inevitable, right? So this is, in this case, I cannot proceed any longer. So this is a singular case. And singular case, I mean by you are not able to get n pivots from the system. Singular case. So this is no n pivot. We will turn to this case later, maybe in next couple of weeks. All right, but that is that. Now, turning to next section, I am in section 1.4. Matrix notation and matrix multiplication. Well, I told you that this lecture is based on the assumption that you have never heard about the matrix or the vectors. So I will Now I will officially introduce the definition of the matrix. So what is the matrix? Matrix is an, well, m by n matrix are usually denoted by the uppercase letter Aij. This is my another notation for the matrix. Just to emphasize that this matrix consists of these looking entries. Is what is a matrix? Is a two-dimensional array of numbers which looks like sorry, I don't want to spend too much time drawing the matrix. So this is a matrix. So clearly this is two dimensionals. And as you can see from this picture, A, I, J. Every entry of the matrix, so each of these numbers in this array, they are called entries. And every entry has two indices. The first index is represent the row index. So which row this entry is located. And the second index, J, it represents the column index. So which column this entry is located. So so a number in i's row and j's column is denoted by aij. Sometimes this is called the ij entry of A. Or sometimes I say the i's row j's column entry of matrix A. This is another notation. So I will interchangeably use all these notations. Okay. All right. So this is a matrix. And by the way, I will also need to mention this number, m by n. So this number, this m by n, this number is sometimes called the dimension of the matrix. And this first number means how many rows do you have? So it's the number of rows of the matrix A. And the second number is the number of columns in the matrix A. So this is number of rows and this is number of columns. And if m equals to n, then the matrix is called square, the square matrix. Okay, so this is my version of matrix. This is my definition of the matrix. And as you can imagine, there are some operations between the two matrices. Operations on matrices. What are the operations? The first operation is matrix addition. Suppose I have two matrices, A and B, that has these looking entries. I have these two matrices, and let us suppose that these two matrices have the same dimensions. They are all m by n. then matrix addition is defined like this. So well, I should say this is an entry by entry wise addition. A plus B ij is aij plus, yes, this is the entry. So entry by entry addition. And well, as we did in the vector spaces, there is a scalar multiplication for any number C. C times A is, well, every entry is multiplied by the same number, multiplied by number C. So this is a scalar multiplication. Okay, nothing is complicated. But this is somehow complicated. Matrix multiplication. So you can multiply two matrices. Okay, I have two matrices, Aij and Bij. Well, when I try to define the matrix addition, and these two matrices must have the same dimensions. So if those two matrices have different dimensions, then matrix addition is not defined, right? But for matrix multiplication, there are some complicated the dimension constraint. There are some dimension constraint on these two matrices. The first matrix has m by n dimension, and the second matrix is n by k matrix. The point is the number of columns of the first matrix must be the same as the number of rows of the second matrix. These two numbers must coincide. If not, the matrix multiplication is not defined. Well, so suppose that the dimension constraint has been met, then you can define a matrix AB, which is a m times k matrix. Defined as the ith row jth entry, ith row jth column entry of the matrix AB is defined as from L equals to 1 to n, A, I, L, B, L, J. Yeah, so this is the definition of the matrix multiplication. So if you have never seen the matrix multiplication before, then this definition must look very scary and mysterious. So I will try to explain how. This is my matrix A. This is my matrix B. And so in order to compute the ij's entry of the resulting matrix AB, then what you're supposed to do is Well, choose the i's law of the first matrix and choose the j's column of the second matrix. And since because of this dimension constraint, the number they all have the n numbers here and there, and you multiply this guy by this, you multiply this guy by the second guy by this, this by this, and this by this, and once your multiplication is once your multiplications are all done, then you add all these numbers together, and that is going to be the number ij's entry of the resulting matrix. So this is the matrix multiplication, right? Well, so if you have ever been to the multivariable calculus course, then I think you might have heard about the inner product. So what is the inner product of two vectors? So inner product of two vectors is component by component, you multiply component by component and add it all together. This is precisely the same computation. Component by component multiplication and add it all together. Then that is going to be precisely this entry. Okay. Well, this is my rule of thumb. So suppose that I want to multiply this matrix by that matrix. This is 3 by 4, and this is 4 by 2. Therefore, the dimension of the resulting matrix must be 3 by 2, right? And to multiply these two matrices, and if you're not that familiar with matrix multiplication, then I draw these horizontal lines for the first matrix and vertical lines for the second matrix. And to compute the 1, 1 entry of the resulting matrix, then I take an inner product of the first row and first column. In order to get the 1 and 2 entry of the resulting matrix, then I take an inner product of the first row and second column, and so on. So once you do bunch of inner product, then you get the idea. Okay. You know how now you know how to multiply two matrices. All right, so this is the matrix multiplication, and also there are some important properties of matrix multiplication. The first property is suppose that all these dimension constraint has been met. Then in this case, suppose that you want to multiply 3 matrices. Then there are 2 options: multiply first 2 matrices first, and the multiply C later. And the other option is multiply B and C first, and multiply by A later. The first condition for the first property guarantees that the order of multiplication doesn't matter. So therefore, from now on, so if you want to multiply more than 2 matrices, then there is no need to put the parentheses every time. So this property is called the associativity. And the second property is the distribution. Distributivity, AB plus AC, and there are 2 different versions of distributivity, and AC plus BC. So this is also true. I will not prove this, but the commutativity of the matrix multiplication is not true. Even if your matrix is A and B are square matrix, they have the same dimensions, AB may not be the same as BA. There is some very interesting counterexample. A is 1, 0, 0, 0, and B is 0, 1, 0, 0. Then A times B is A times mm, 1, 0, 0, 0. So 0, 1, 0, 0. And BA is mm, 0, 0, and 0, 0. So they are not the same. Okay, so in general, the matrix multiplication is not commutative. Okay. Now some special matrices. The first special matrix is a column vector, or sometimes I say column. Is what? This is just n by 1 matrix. So this is a matrix that only has exactly one column. So you have seen this, right? So this is a column vector. And likewise, I have row vector, or just simply row. Is an 1 by n matrix. Okay, this is column and this is row. They are very special matrices. Well, using the notion of the row vector and column vector, I can think of a matrix multiplication in this way. Suppose that I want to multiply these two matrices. This guy has dimension n by n. This is n by l. Okay. Instead of just multiplying these two matrices, but here, let me consider this matrix B as a collection of column vectors. What do I mean by that? Well, I draw these vertical lines just in order to emphasize that this is a column vector. So each of these column vectors consists of n entries, right? So the first column vector contains B11, B21, B31, all the way up to Bn1, right? Then the second column consists of entries B12, B22, B32, all the way Bn2, like this. So, well, I can view this matrix, as a collection of column vectors. Is it okay? Well, if I do that, then the resulting matrix AB can be considered as like this. Oh, hey, what is this? Oh, okay. Let me consider the dimensions of these vectors, these matrices. A has dimension of m by n. And what is the dimension of this B1? This is n by 1, right? So m by n multiplied by n by 1. And this is what? This is m by 1. In other words, this is an m-dimensional column vectors, right? So in other words, this resulting matrix AB can be viewed as collection of L m-dimensional columns. Okay? Right? No? Okay, then what about this? Okay. Or well, I can view my matrix A as a collection of m row vectors and then the resulting matrix is A1 times B. This is still row vector. So this is how we usually, so this is how we view matrix multiplication as bunch of, sorry. Sorry. If you do not feel too comfortable with these notations, but just leave it like this, okay? Because this is not needed immediately. So, okay, why don't you just leave it and go turn to the next topic? Sorry. The next very special matrix is the identity matrix. So what is the identity matrix? So identity matrix is a square matrix and whose diagonals are all ones and otherwise zero. So this is identity matrix. So this is n by, well, this is an n by n matrix whose diagonals are all ones and all and every other element entries other than diagonal equals to zero. This is the identity matrix. And I write I sub n. So I put n just to emphasize the dimension of the identity matrix. But if the dimension of the identity matrix is clear from the context, then sometimes I drop the subscript n and I write I. Then this is very important properties on the identity matrix. For any matrix, A and B, as long as the dimension conditions are all met, then A times I is IA and I times B is B. So in other words, the identity matrix is the identity element in matrix multiplication. Okay. And there are another one, the elementary matrix. Identity elementary, they sound the same, but well, they are different. EIJ is a square matrix such that all diagonals are 1 and ij entry is, it could be any number, right? It could L could be 0 or L could be any number. And number 3, all the other entries equals 0. So this is an elementary matrix. So elementary matrix is so I mean identity matrix is a very special elementary matrix, right? Identity matrix is an elementary matrix whose L value equals to 0. Okay, so this is an elementary matrix, and why do we even care about the elementary matrix? So there is very interesting properties on the elementary matrix. Yeah, suppose that I have n by n elementary matrix Eij, and this guy is being multiplied by, on the right, n by 1 column vector. Okay. Okay. Let me be a little more explicit. So this is my Eij. This is my elementary matrix, and this is the column vector. And I have in i's row and j's column, I have some number L here. What if I multiply this by this? The resulting matrix must be another column vector, right? And this resulting column vector is almost the same as the original column vector, but there is only one difference. What is that? Well, this i's entry of this column is now changed to L times Bj plus, well, there's invisible 1 here, right? L times Bj plus Bi, right? Right? Agreed? Yes. Once you're all good about this, then maybe I can generalize this step even further. This time around, the elementary matrix Eij is not multiplied by a single column, but multiplied by n by n matrix. Now let me see what is happening here. Then Eij being multiplied by this. Well, here I consider my matrix A as collection of row vectors. N collection, well, I have n m-dimensional row vectors. N m-dimensional row vectors is consisting the matrix A. Am I right? Now, for a single vector, multiplying by elementary matrix resulted L times the J's component plus I's component. And because the same logic, if I multiply this guy by this, then the resulting matrix is going to be another m by n matrix. But everything is exactly the same as the previous one, A. But J's element, but I's row has been replaced by L times J's row plus the I's row, right? Then this, okay, why do you even care about multiplying by elementary matrix? And if you're paying enough attention to my lecture, this procedure is exactly realization of the elementary law operations. But everything is written in terms of the matrix. Right? So elementary law operation can be mathematically written as a matrix multiplication, especially using elementary matrix. Okay. Okay. But this is for today, and I will see you on next Tuesday. Bye.